Problema del director.
Now.
You have your microphone open.
No.
No, he doesn't. He doesn't have it open. Only we do.
Is it okay?
He doesn't have it open.
We have all kinds of projects.
Only this one is.
Since 2013, he has been a researcher at the UNAM Instituto of Astronomy in Mexico, where he's a senior researcher C, which is equivalent to professor, full professor, and he has also been a senior scientist on leave from the AS5. Throughout his career, he has received numerous awards, including the level 3 of the Mexican National System of Researchers and the highest institutional evaluations both in Mexico and Spain. He is among the most cited astronomers in Mexico. Should say Mexico. His research focuses, His research focuses on the evolution of galaxies using integral field spectroscopy, and he is a pioneer in the development of analysis techniques and tools that are widely used today, and I'm sure some of us have already used. He was the principal investigator of the here at the IAA well-known project CALIFA, which was the first large-scale survey of its kind in the local universe, whose results transformed the study of galactic evolution and laid the foundations for subsequent international projects such as MAGA and SAM. He has published hundreds of high-impact scientific articles. In fact, the research that rapidly made yesterday through the ADS, I counted about 450 or more than that papers with more than 32,000 citations. Including an invited review in the Annual Review of Astronomy and Astrophysics. He has supervised more than a dozen doctoral and master's theses and trained a generation of young astronomers in Mexico and abroad. He has led multiple scientific, instrumental, and software development projects, and he currently heads the International Local Volume Mapper sampling with SLOAN-5 and maintains an active scientific outreach effort, including daily content on social media. So thanks a lot, Sebastián, for being here and talking today about the local volume mapper sampling. Thank you very much.
Well, after, will you hear me? Yeah? Okay, after hearing this, I'm a bit overwhelmed to give the talk. First, thanks a lot for inviting me home. Somehow I always feel home in this institute to give this talk. This talk is a bit different of what I used to give because it's a kind of a mix between different contents. I'm going to talk about the current SLOAN-5. I'm going to talk about main focus on the local volume mapper. That's a program that I'm actually leading eventually. And what we are thinking for future in the what we name after SLOAN-5, that is basically eventually I would hope it will become SLOAN-6. So, well, let's talk about give talk. Now this is not working, obviously. So, what's a SLOAN? The SLOAN Detailed Sky Survey is a project that basically has different epochs or different periods. It started the first session, let's say, started in the year 2000, and it has been living for the last 25 years. It was not the first, but essentially was the pioneering in a different way of addressing astronomy observationally, because basically in the last 100 years, we have been doing astronomy with a group of a small group of colleagues that propose a certain project, go to the telescope, train the students, and get the data for themselves, and then the data somehow die around desk or around computers. SLOAN was one of the first surveys that was conceived as a legacy for the community. So it was a transversal observational project with different scientific goals, and was from the beginning trying to make data accessible as easy and as broad as possible for the full community. And this has changed the way we do astronomy from a handwork to an industrialized method. In all the projects that are now around, DAISY, Gaia, whatever, have in their roots this fundamental concept that Sloan have imprint. Has democratized astronomy because it has made people that have not access directly to the telescope access to the data and doing science with this data. But beyond that, it has created a way of doing science. So it has created an infrastructure where young astronomers can develop themselves and doing their career. And this is extremely important in the core of Sloan. Once you have been working in Sloan, you realize that the spirit of collaboration is completely different from many other projects. In the different sections of Sloan, it has been addressed the observation of the sky in different ways, from multi-wavelength photometry that we know the heritage of the first Sloan session, a single fiber spectroscopy. Then, after a certain moment, they jumped into doing interference spectroscopy with the Sloan 4. It was focused on the largest IFU survey in terms of the number of galaxies still existing was MANGA with 10,000 galaxies observed. They have been focused in the analysis of different science topics, from basically stellar evolution to black hole evolution, AGN processes, galaxies evolution, and cosmology. All these things have been addressed in the project. And now we will focus on the Sloan 5, that is the project that is currently going on, that have 3 major surveys: the Milky Way mapper, the black hole mapper, and the local group mapper. This has been translated to a big impact. It has been a tremendous impact in the community in terms not only in the number. I could put some numbers just to highlight the impact of this survey. They have more than 10,000 articles and 800,000 citations. But it's more relevant to me is the international network that has been built around Sloan. So when you work in Sloan, you work with people of a very different audience. And it's very important because you get input from people that normally you don't address. Just because the project is transversal. There are experience in techniques, experience in the way that you address the things, experience in the way that you distribute the information that you will never have access, because simply we talk normally with people that we work in our own topic. This is translated in particular to the small institutions like the one that I am currently working in, the Institute of Astronomy at UNAM, that we realize that we are in a small institute compared to other institutes, especially in terms of budget. This gives us to a tremendous impact abroad, and the ability to generate for young researchers, some of them are in the audience or no, the impact that they have, it was impossible to achieve. And this is the sharing from Sloan 4 of articles that have been led by the Institute of Astronomy. Now, this would have been impossible without being part of this kind of collaborations. But it's even beyond that, the impact that the young researchers may have in this kind of projects, it would be also impossible if they were not part abroad. So this allows us to participate in the distribution of data that has been used. This is part of the democratized the access to the data to other people, and also have feedback on our own community. So I want to extremely highlight the importance of being part of these kind of collaborations for the impact that you may have in the future. The current Sloan 5 that is led by Una, that's the picture up there. If you are interested, she had very nice talks in TED Talk. It's a Sloan 5. Sloan 5 comprises 3 different surveys. The Milky Way Mapper. Milky Way Mapper is a continuation of a survey that you may know, Apogee and Apogee 2, that was focused basically on the exploration of the stellar properties and the evolution of the stars to understand the evolution of the Milky Way, the galaxy evolution of the Milky Way, and the chemical evolution of the Milky Way. For the first time, the Milky Way mapper maps 6 million of stars so far. It has still 2 years, year and a half of getting more data. And with the combination of infrared spectroscopy, super high resolution infrared spectroscopy, together with optical spectroscopy, that combination is unique. Then we have the black hole mapper. The black hole mapper is basically focused in the exploration of the growth of black hole and the characterization of black holes and the alien activity. Has the unique combination of Rosita South with optical spectroscopy of the order of 500,000 ADNs and galaxies. There are people in the audience working with this data. And the project that we are, that I'm currently more actively working is the local volume mapper. That is exploring, it's the first IFU survey focused on the Milky Way and the local group. And it's exploring the star formation process, the feedback process, and the chemical enrichment in our galaxy, obtaining at the end, we hope to observe, we have observed half of that, 50 million spectra in a continuous way of 300 degrees in sky with a resolution of 4,000. This is the instrumental setup that we are now running in the SDSS-V. And these are tiny telescopes. These tiny telescopes are the one that we are running the local volume mapper. It's 16 centimeters. There's that side. They're really very small. And we are sampling basically the Milky Way, the Magellan Clouds, and some local galaxies. You are more interested in this panoptic exploration of the sky. This is the article of where this is described in more detail. Contrary to other versions of the SDSS-V 5 also comprises a lot of instrumental development. For the we had changed due to the density of targets that we are exploring from previous versions of SDSS-V 4. This is the density of targets in SDSS-V 5. We have changed completely the technique that it's how we explore the sky. In the case of the Milky Way mapper and the black hole mapper, and there are people in the audience that will work in this technical part. Instead of the previous way, where this kind of they are aluminum plates that do black manually the fibers of the IFUs. We have changed for Magnus robots that make a very fast response. For the first time, we can explore the sky in a very for time evolving type that we will explain later. That came at a cost in time, cost in development. And in the case of the local volume mapper, we developed a completely new infrastructure that is based on these 60-centimeter telescope that they're up there. They were installed in the outside garden of Heidelberg MPI Institute. That was October 2022. This was observations were starting in March 2023, installation in Las Campanas in Chile. And now we have collected 36 million spectra with that Magnus machines. So what is, I'm going to focus on the local volume mapper a bit more. What is the local volume mapper? As I told you before, these are the key people that were leading that, and majority Guillermo Blanc, Catherine Carroll, Ellie Johnson, and I want to mention also Alfredo Mejia, that was making a lot of work in this project. It was the first IFU survey focused on the Milky Way. You cannot find that also in the Magellan Clouds. This is the kind of data we are taking. We are observing with a huge IFU. Each of these hexagons correspond to one point of the sky, and the size is the size of the moon. We never had an IFU that big. Well, of course, this came as a penalty that each fiber, and each IFU comprises 1,700 fibers. Each fiber has 30 seconds of aperture. So basically, each manga pointing corresponds to one single fiber, or each Khalifa pointing will be 4 fibers or 5 fibers. And this was the what we had completed in the sky like 1 year ago. I will show you what we have now. And the main focus is to explore in a multi-scale, because since we have a fixed aperture in the sky, That basically means that the targets that are nearby, we are exploring at the very high resolution of 10 parsecs, and the targets that we are a bit far away within our galaxy, we are exploring at the order of 50 parsecs. If you are exploring the Magellan clouds, we are going from 20 to 100 parsecs, and if we go beyond and go to M33, we are going to explore at the order of 200 parsecs. So this is a multi-scale exploration. It's focused on to resolve, explore the feedback processes and the injection of energy and the chemical diffusion at different scales. So why we need the local volume mapper? Well, we came from the extragalactic exploration using IFUs from a different perspective. We were exploring galaxies both either as integrated entities or non-resolved entities. In the last 15 years, we entered in a phase where we resolve the galaxies, we resolve the galaxies using IFUs with resolved spectroscopy, and this provides us with a way to explore the air, the morphology, the gas content. That's a map of oxygen 3 in blue and H alpha in green and nitrogen in red. In a map where we are showing the star formation rate versus the stellar mass, and you see the star formation sequence very well traced by the galaxies that obviously are blue and are currently star forming, and then you have all these sequence, this cloud of retired galaxies. We could explore the gas content, we could explore the kinematics, and the obviously is different from one galaxy to another, and the stellar content. And we know that these galaxies here have more presence of younger stellar content than these other galaxies that lack, they are retired there. And we have explored how this process happens in the quenching of galaxies resolved from the inside out, and how the chemical the abundance gradient is telling us how galaxies are growing. All these richness of information came from the explorations we have performed using Khalifa, Manga, and Sami, that were basically observing the galaxies at a spatial resolution, spectroscopically, at a spatial resolution of the order of 1 kiloparsec. Okay? One of the things that emerged from these explorations is that the galaxies, especially star-forming ones, follow very tight relations that can be can emerge from integrated quantities when you compare the star formation rate of the galaxy integrated through the galaxy with the stellar mass and the star formation rate with the molecular gas. They follow very tight relations. This is shown, this global extensive relations are shown in the upper panels. In blue are represented the galaxies that are currently forming stars, and if you just look at the blue, the sequence traced by the blue galaxies, you can see that there are three main relations: the star formation in sequence, the Smith-Chemical law, and the molecular gas main sequence, that are relations between these three integrated properties. When we explore the galaxies spatially resolved at down to the scale of 1 kiloparsec, we find resolved versions of those relations that are, instead of extensive, are really intensive quantities between the surface density of the star formation rate and the surface density of the stellar mass, the surface density of the star formation rate and the surface density of the molecular gas, and the surface density of the molecular gas and the surface density of the stellar mass content. And that resolved intensive relations are held at any scale within the star-forming galaxies when you are above 1 kiloparsec. So this is represented in this cloud of points. The cloud of points came from a project that is the Khalifa. This is a follow-up of molecular gas content spatially resolved to about 2 to 3 kiloparsecs in the Khalifa galaxies. Each point corresponds to one of these resolved regions that are currently star-forming, and clearly they follow three well-defined relations. But what you see in contours are two different spatial regions. What we label here Califa is the integrated area of the Califa galaxies, and what you are seeing in blue is the core, is the contour density of integrated galaxies. So each point in this coordinates correspond to one galaxy. For the full galaxy area, you take the full star formation rate, you divide by the area, and you put a point in there. The apex is an observation with a single dish millimeter telescope that the graph just of the order of 10 kiloparsecs. So from 1 kiloparsec or 2 kiloparsecs to 10 kiloparsecs to the full extension of the galaxies of the 30 kiloparsecs, the relations that you find are exactly the same. And actually, when you integrate these relations, you end up with the relations that you are finding up there. That basically means that the relations that regulate the star formation rate in galaxies, and I didn't put another relation that is the mass metallicity relation, but you have exactly the same kind of pattern. So both the star formation and the chemical enrichment is ruled or controlled by a set of relations that hold from a 1 kiloparsec scale to an entire galaxy size. This was a novelty among the different novelties that were uncovered by this kind of surveys. However, we know that these relations break below a certain scale. When you go well below the kiloparsec, the relation disappears. And that was very well illustrated by this article in Christian et al. In 2019, where they explore a very simple thing. You take a maps of H alpha and maps of that you can transform to star formation rate, and maps of CO that you can transform to molecular gas surface density, and they try to trace the ratio between the integrated star formation rate and the integrated molecular gas mass at different apertures that trace different spatial scales within the galaxies. They started these apertures in the peak of the molecular gas context, that was the points in blue, and in red, they start these apertures, these concentric apertures, at the peak of the H alpha intensity. And what they found is that the ratio converges to what is expected from the Smith chemical law, only above 1 kiloparsec. Exactly the regime that we have sampled with Califa and Mangel. But there is a regime where these relations that don't hold. The relation disappears. And it's some kind surprising, but it's not surprising, because the current molecular gas content that you are measuring cannot be the one that is inside the star that you have formed. So you think about, it's not that surprising. The molecular gas content that has formed the current stars that we observe is a molecular gas that you are not observing anymore because it was in the molecular clouds before, not now. The point is then why this relation holds, why this relation exists. So going further, we found that the three relations that I have described before can be described in a three-dimensional space as a single time relation with predict the star formation rate with the hidden quantity, that may be the combination of the other two. And if you go to some theoretical exploration of Stryker et al., this hidden parameter, it's a type or represent or trace the pressure in the disk of galaxies. So basically, what we are seeing here is some kind of an equilibrium between the energy injection produced by the star formation rate and the pressure that the disk is supporting. And for an equilibrium to happen, you need a time. The time of star formation rate we know, more or less, our length, a molecular cloud transformed to stars, and a scale for propagating the pressure. And these two combinations end up basically, if you take into account the typical speed of a wind that is produced by supernova explosions, for instance, you end up with some kind of a scale of between 0.5 kiloparsec and 1 kiloparsec it will be the scale where this equilibrium starts. So that's why, or that's why we think that the current relation that we have seen at 1 kiloparsec, they don't hold at the smaller scales. And here is where the problem starts, because that means, okay, now we have the idea that pressure and equilibrium is and feedback from the our star formation regulates somehow the process of star formation in galaxies. But we also know that star formation does not happen at the kiloparsec scale. It happens at much smaller scales. So for individual stars, obviously it happens at the lower scale of the parsec. And for small molecular regions, molecular clouds, you have the order of a few parsecs, but then you have and all the bulk of the star formation that happen in galaxies that obviously is not homogeneous. That happens between 100 parsec and a total 12 kiloparsec. So we need to explore the physical processes well below the typical scale that we were applying to understanding the evolution of galaxies using the current data set that we have with integral field spectroscopy. And this is where the local volume mapper really is, or what the local volume mapper is after. Exploring the stellar feedback at the energy injection and the diffusion, the chemical diffusion at a scale well below the scale that we have explored before to really understand the physics that is behind these relations. So feedback is a key ingredient. I hope I have convinced you for understanding the scaling relation that we have uncovered using previous IFU surveys. Feedback is also behind the Riesman process in the interstellar medium. Feedback may guide the expansion of the star forming region, the disruption of the molecular clouds that generate the new set of a new the cocoon of a new star formation, regulate the formation of stars, and in a sense, the baryonic cycle is tightly related to a feedback process. So then we embarked to this survey with the main aim to explore in a multi-scale way that is, as I said before, the objects that were nearby will solve a very high resolution of the parsec, and the object that we observe farther, we will reach a resolution that's 10 times better than what we already have from the current IFU surveys. And for doing that, we are centering now in this epoch of the project in the south hemisphere with this super high wide field IFU that cover the entire size of the moon, because if not, we cannot cover such a huge area. And we developed this marvelous infrastructure. This is formed by 4 telescopes. 2 of them are just for sampling the sky. The sky is a problem when your target is as big as the sky itself. This is the whole galaxy. But if you want to talk about events, I can tell you later. One of them is holding the IFU, and another one is just made for calibrations. And these 4 telescopes are connected by fibers to 3 DESI-like spectrographs that have 3 arms, a blue, a red, and an infrared one. We provide the spectroscopy of covering the optical range from 3,600 to nearly 10,000 angstroms. And with this data, this unique instrumental setup, we are going much at a better resolution than what MANGA provide, of course, better than Califa and better than Muse. We are covering very strong, the typical strong emission lines for the exploration of interstellar medium from option 2, 3,726, 27 to sulfur 2 in 9,500. And we are also covering very weak aurora lines and very weak recombination lines. So we are having access to the temperature derived by the Dirac method, and the temperature, and also by abundance derived by the recombination lines in many cases. density measurements, we can address problems, fundamental problems like the abundance discrepancy. And the instrument is very stable, having high quality signal to noise and flash calibration. Sky is an issue that we are addressing, as you may imagine. All this data is complemented with a huge data set of ancillary data, the multi-wavelength information coming from atomic information, molecular gas information, dust. There are many surveys that complement, we are covering the Magellan Clouds, and there are many surveys that complement that with HST and with other ground telescopes. We have X-ray access. Eurosita is covering all our observations in the south. And we have complementary information from Gaia and APG and Milky Way Mapper and so on. So I want to highlight the interconnection between different projects in the SLOAN. In this plot, I show you what the Milky Way Mapper is sampling in this idealized distribution of the density of tiles that have been sampled on top of what it should be the distribution of our galaxy. As you can see, it's covering a fundamental area of what we are covering. So we have a lot of complementary information that allows us to explore not only the emission lines, but also the stellar content in the field of view that we are sampling. This is an example of what you can achieve when you have a super high field. This image here is what we shared with TPAC in 2007, 31 pointings in Orion. What you have at the top is 81 pointings with Muse, and all this is basically that tiny region in here. Okay, this is the coverage that we have. This article from Catherine Kerr, 2024, is 1.5 years ago. It's showing for the first time the spectroscopic content of all this huge area, and understand how this is a huge bubble that cannot be traced with any other instrument in the world. So this is one pointing of the LVM, and this is the area that was covered by TPAC on one single spot. Of course, the penalty is the spatial resolution. But if you want to understand the feedback process, you need to know where the image injection goes, and you have all the stellar content at the same time, so you can connect the energy. So this is the kind of spectra that you are getting with the local volume mapper, and this is the center of Orion, this area here integrated. And I want to highlight the Passion break, Balmer break. Oh, this is a H1, H22. You know, all the full sequence of Passion lines and the Balmer lines. We can see also the resolution allows you to measure the winds on the lines of Orion. That is related to the physics in this, and that's Aurora lines. You know, it's Oxygen 3, 4363, Natrium 2, 5752, and this is a sulfur free 6301. So all these are temperature indicators. The advertising, since you have this multi-scale thing, you can integrate and stack and get the spatial result information on the temperature and so on. Of course, obviously, for digesting this enormous amount of data, you need to develop your own software. And this is also a very niche opportunity for young researchers to get involved in this kind of analysis. You need to realize that since we are sampling the objects at different scales, we cannot apply the usual techniques that the people use when they use resolve spectroscopy and you tag individual stars. And at the same time, you cannot use the synthesis method that we use in IFUs when you sample them at the 1 kilopascal scale, you are in between the two things. And so sometimes you are sampling objects. This is not a bad thing. Each of these points is an apogee star. So basically, there are objects where you resolve individual stars, and you can use the usual techniques to tag them and derive the temperature, gravity, the abundance, and the metallicity. But sometimes when your target is a bit far away, then you just don't resolve the star. You are in some kind of a partial resolve. This what Neothelio used to work, that you need to apply some stochastic techniques or a different technique where the population does not have a certain particular property, but the distribution of properties or probability distribution function. So we develop a different approach. I'm not going to enter too much in details about that, but you need to develop a new way of analyzing that, where instead of working with integrated unresolved populations or resolved stars, you need to handle that in a more probabilistic approach. This is the workflow of the organizing pipeline. I don't want to enter too much on that. We recover the properties, make simulations to test that we are recovering the properties thoroughly. The most important thing is that out of that, there is a bunch of articles that are getting out, analyzing and using both the data and the analysis tool. In the background, I'm showing you the current distribution of pointings. We are covering half of the proposed area right now. It's 15,000 frames, 26 million pointings, and this is different articles in the Mercure nebula, in the Magellan Clouds, supernova remnants, H2 regions, super bubbles around H2 regions, planetary nebula. That is led by a bunch of people. I'm not going to say all the names, sorry. And it's really interesting to show you what we have already covered. That is in blue. Well, this is an image of September of last year, and this is what is still to be covered when we finish the survey. By the end of this year, we will deliver some hints of what is in this data set: the center of Orion, the center of Rosetta Nebula, the Lagoon Nebula, and some galactic targets. And this is still proprietary, so the people that enter now in the survey, is an opportunity of entering now half of the price. We will have a priority access to all this data set. But as I told you in the beginning, this is what is going on. But we are going to start the new set of the SLOAN survey. And in this new set of SLOAN survey, we have been approved these 4 projects: the Hidden Galaxy Explorer, the Dynamical Universe Explorer, the second version of the Local Volume Explorer, that I will tell you a bit more, and the Atomic Genesis Explorer is going to be led by Keith Hawkins, that is the PI or director of the new initiative. The Hidden Galaxy Explorer is, in a sense, is a continuation of the Milky Way mapper, but it's going to explore individual stars in the infrared, but on the side of the galaxy that has never been explored, because it's at the other side of the disk, at the other side of the bar, the central part of the galaxy. This has been totally unexplored, and we have a lack of knowledge of the evolution of the galaxy. And it was a revolutionary jump between apogee, it was the density distribution of apogee, to the density distribution of the Milky Way mapper. And today, imagine that this is going to change also perspective, because that other side of the galaxy has never been explored. We have the Dynamical Universe Explorer. It's a continuation somehow of the black hole mapper, but not completely. And here are some people in the audience working in the evolutionary chain of AGNs using the time data set, the time evolving data set that we were observing with the black hole mapper. Now we are using these abilities that the robot provides us to rapidly answer to transit events, to make follow-ups, for instance, of the LCCT and the SDSS-V telescope that are going to provide thousands of supernova, tidal diffraction events, tracing asteroids, any kind of variable target will be addressed in a second with this super machine, and that's what the dynamical universe explorer is after. And of course, we will continue with the observations of aliens, taking the spectra for 2 decades already. So we're going to trace the aliens in 2 decades time. And this final, apart of the local volume mapper 2 that I will explain more, this final project that is a total novelty, the Atomic Genesis Explorer, it's focused on exploring for stars the chemical abundance, relative chemical abundance for atomics, for elements that has never been explored. These are the distribution at the different, the size correspond the number of stars in the Milky Way mapper, and this direction is how the abundance, relative abundance change. And what we have here is the elements that has been sampled by Apogee 2, and the Milky Way mapper. And all these elements, we have no clue about how the chemical enrichment happens from the empirical perspective. They are going to observe a reduced number of stars to a very high depth with a resolution of 70,000. So it's a totally different way of addressing these problems. And finally, the second version of the local volume mapper. The second version of the local volume mapper has 2 projects. The Interstellar Medium Explorer is basically continuing the effort that has been done for the with the local volume mapper. We are going to continue serving the same target to a very high depth. So we're going to use the infrastructure that we already have, and we're going to start to integrate until we have a super high signal to noise in the recombination lines, trying to solve the AF problem. That it's basically what we want to highlight in here. That it's basically where I'm in the south. But then in the north, we need to develop a new infrastructure for what we name the local group explorer. The local group explorer is going to sample all available dwarf galaxies accessible in the north to 10 megaparsecs. These are the red squares. So we are going to explore a regime that has not been explored systematically with IFUs never before. And we are going to set also M33, that is a super dwarf, and M31, the basic laboratory for the chemical enrichment and star formation process, because it's the partner of a Milky Way, the most similar galaxy that we have accessible to explore. And we're going to cover the entire, we make a full map of up to 1.5 R25 of the Andromeda galaxy. So it's just to illustrate where is the connection between the different scales. This is a data set that we took as an experiment with manga infused. In the left, and it's we sampled with nearly 500 pointings this galaxy, this IC342, and each fiber in the manga infused covering this at the distance of this galaxy correspond to 40 parsecs. So we are in the regime where I told you that we are not. We are not in a regime where the scaling relation holds. But each fiber has a projected, each IFU itself, projected at the distance of this galaxy, have a size of the order of 1 kiloparsec. So by comparing these 2 regimes, we are in a sense exploring this transition between when we are driven by the equilibrium of the feedback, or we think that this is what is happening, and when we are driven by the physics of the star formation process itself. So we are still analyzing these data sets. We have produced a first set of articles. And the problem is that this is a single galaxy. With the local volume mapper, we are going to have a bunch of these galaxies. And that's where statistics holds. So let's illustrate a bit more. This is an effort that other people in the audience may recognize, no to them. This is the largest IFU survey that we have so far in M31, and correspond more or less to that area up there, a bit less than that area actually. We have a lot of data at Gaia. This is the distribution of the density of stars observed by Gaia on that galaxy, but we don't have a similar exploration using of the interstellar medium. And what we aim is to observe the entire Andromeda. And for doing that, we need to develop a new instrument. We have the spectrograph, but we need to develop a new IFU, and it has been proposed for 5 telescopes. One of them is almost discovered. There are 5 telescopes, and one of them, and that's why I think this talk is relevant. You may recognize that's 2 meters in Calar Alto. So one of the candidates is a very, very good candidate, and we're aiming to install the spectrograph in there for performing that in a survey that we will start somehow in 2018 to 2028. So that's my last slide. What do you need to take away and how? I sincerely think that Sloan has been, and it still is, one of the most exciting projects that you can get involved, especially if you are a young researcher. Sloan 5 is progressing very well. We have already delivered the year 19. For the local volume mapper, we just delivered 1 pointing because we were not prepared for that. But in this year, we are going to deliver of the order of 400 pointings out of the 15,000 that we have in this. We have covered half of the spectral observations, and we're really going very well in the data production that I said earlier. So internally, people have already access to 15,000 to 26 million spectra, and they are effectively working very nicely on that. And we are really looking for partners for the new generation of the local volume mapper and the after Sloan 5. We really think that this kind of transversal projects are very important for institutes like this one that are addressing a lot of different science cases, and most probably in the audience you have seen niches where you can contribute and you can benefit from this kind of data. That's one of the reasons I came in here. So if you want to get involved, you're more than welcome, because we need a lot of manpower to work on these projects. So, wow, it's the first time I finish in time because I throw many things out. So, thanks a lot.
Well, we have time for questions, even if it's late in comparison with other colleagues. So please.
Wow.
Just a very nice question. Do you think that modern technologies related to artificial intelligence would be necessary for addressing such kind of huge amount of data?
Yes. I mean, the short answer is yes. The long answer is that we have a problem even for visualizing this, not only for analyzing it. You say, okay, you have all these maps, and there are people in the audience that have been working how to visualize these things. So how to present them to the people? That's really a big effort. I had to open a screen of that, but I cannot show you because the network was broken. So there is a team that is developed just to visualize these things, to analyze that with the new techniques. Yeah, the multi-scale thing is something that we are not prepared. I mean, if you go to classical architects, for instance, Orion, they were looking just either to the center of make maps of a certain narrow band, but they hit this bubble, but they had no information about the spectroscopy. That was impossible to that. To connect scales, so there will be things that are connected physically that we cannot imagine because we didn't have a way to handle that. And AI will handle that, they handle that. But we need a computer that have the ability of log all this information at the same time. So it's not only a question of technique, it's a question of computing power. But yeah, totally agree. I mean, I think this data, we are going to take out the cleaning of this data set. But it will take a lot of years to really dig into that, and AI will be really necessary. Yeah.
Related to that question, the problem of the volume of the data. I mean, so far, people have been downloading the data, manga, whatever. But in the future, I mean, this is huge. A lot of amount of data. So is ready of the machinery, I mean, for the people to work when the data is available publicly. I mean, how is it going to be the process of the?
Well, I'm surprised about the ability of computers to grow faster than what we imagine. And there are people in the audience that have been created huge, not a huge, because some of the point is have different. So we're people is creating cubes with that. And you have machines with 1 terabyte of memory to digest that. Yeah, it's true. And it's complicated. So decentralized analysis is something that we really need to think about in the future. The people will be unable, especially if you start to do multi-volume things. So for example, we overlap totally Gaia, and the Gaia is still about formula. But SPHEREX, if you want to go in each fiber, each point, and connect the optical spectroscopy with the infrared spectroscopy at the same time, analyze that at the same time. Yeah, it's on the table. But it's challenging, but it's encouraging for young people. Yeah, I mean, we thought that we'd have everything solved, and it's not. And beyond that, to understand the physics and how to make a model in subgrid, how to make really fully consistent and going beyond, that's, I think, is one of the key problems. Going beyond the prescriptions that we inject in hydrodynamic simulation for understanding galaxy evolution and doing a self-consistent treatment of these processes at any scale. But computationally, it's crazy, no? But yeah, I don't have the answer.
But that part also, that is something that is also very, not obviously, but is something that the S1 is also trying to push, is that a lot of this is the hard part. The other part is, for example, the documentation, the software deliverance. In this, from the beginning of this law, they work very hard in order to develop tools in order to download this and visualize that. For example, in the case of the local volume mapper, there is a tool that you can see, for example, the pointings, and if you want to download one specific spectrum, not all the several spectra, but one specific spectrum, you can download that.
Let's say if I mean,
yeah, but if you want to do machine learning, you need all the data.
Yes,
you need all the data. I mean, it's almost impossible for people all over the world to download data.
Not necessarily, because then you can, for example, make an script with reversing and then try to download, for example, set of tailings of the data. For example, if you are interested in the LMC, and in the specific of the LMC, you are interested in the Trinca Dorados section, then you can download all this section, and this section is more or less 1 terabyte. And the time of download is 1 terabyte is more or less than 2 days. Therefore, it's accessible in terms of computing.
This is a bit of a disclosure. I'm not going to show you beyond that because I'm not entitled to show you more than that. That's the Orion region. Okay. And if you go deep, deep, and deep. This is the H alpha intensity, and I'm going to go beyond that, that every point in here has a spectrum. That's all, right? So how to handle and guess that, yes. But Sloan, one of the beauties of Sloan is the documentation, data access, they were the frontier of how to do that. There are other people that were following that. So I'm pretty confident because even in our tiny group, there are people developing techniques that for me were like a dream before, you know? Like for instance, fitting the cube in a row. And you see that this barrel thing that is making that for a millimeter data. They are doing that with high field data. They feed the cube entirely and created a model of all the points at the same time. These kind of things happens within this kind of collaboration because the people is pushing in that direction. But then you need to document, distribute, and doing it accessible to the rest of the people. This forces you to be very consistent, and you know there is a lot of barriers in there, and this is challenging. But at the same time, it's really very people learn a lot from that. So if you want to learn all these things, Sloan is really the cocoon where these things happen. And we are not the only one, but actually, yeah, it's important in the community. Yep.
There's a question on Zoom from Rodrigo del Marino, and they say, in order to get involved, as you stated at the end, what are the ways and aspects? Can you explain these details further? Are you asking for data analysis, data reduction pipelines, or is it more instruments?
The answer is yes. I mean, in any aspect, we are short of manpower. You may imagine that Sloan is like a big
Person
machine.
power, please.
Sorry?
Person power,
Person.
Yeah. Human.
whatever.
Yeah. Okay, this is true. I'm sorry. That's a wrong news. Okay. Well, yeah. Person power. Astronomy power, brains, and yeah, I learned only one version of English. Just reform that. No, I totally agree. But yeah, and how do you get involved? If you have expertise on something, and you think that you can do better what the Sloan is doing, you can always raise a hand and say, if your institute is involved, obviously you are entitled. If your institute is not involved, then if you have an expertise and you think you can do better than what we are doing, or the people in the team is doing, and you tell us that you can do it better, the doors are in general are more open than what you think. Because to be a frontier is deny access to people that are better than you. It's really stupid. So people, but yeah. So you know what I mean. So when you want to get involved, you have an idea and you want to get involved. Just address us, and let's see the answer. If it's not covered by the collaboration, surely we will not hesitate to give access to people that have. Of course, if you are in the institute that is member, and now we are offering a possibility to access now and to get involved in the after Sloan 5 and the Sloan after Sloan 5 for half of the price of what the institute used to pay, because we are collecting support, and that's also a possibility. Go to your ruling ruling system, I know the director or head of the department say here, I really need to get involved in that.
Half of the price, how much is that?
It's still, I mean, I cannot tell because the price is still not decided, but anyone that is going to have access later on, oh, come on, UNAM, we never say that in UNAM. So if UNAM, we could enter that, I think this is something that is affordable.
It's not only that you have the money, but you have the right process to use that money for.
Yeah.
That means,
Yeah. It's not, when I tell contribution, it has not to be money. I mean, if you put a telescope on the table, obviously you don't need to put money because you're putting a telescope. If you put the expertise on the table, then you don't need to put money. You have the expertise. So money is is the way we share things, but actually money is not it's not the only way. If you are the very much expert in something, you surely have those more open that you have nothing to offer. That's a different thing.
So the choice for the final telescope for the north will depend on what particulars?
Well, okay, there is a committee that is going to visit Calar Alto the 14th of March. That is going to visit also Tenerife for another telescope a few days before. And they are basically now gathering the information of technical information. And it's going to be driven basically on two reasons. So the first is the technical. So it's the best choice for the product. And the second, this telescope have the support of an institute behind that want to do science, that we can guarantee that we don't put the spectrographs in there and they close the telescope or they evaporate and we don't have the data continuity in the slow is fundamental. That's why most of the surveys are down in the Pacha point, just because it's their telescope. So they can guarantee that it's run as the project is run. So if these two things happens at the same time, and you may imagine why I came here, then it's not only the 2 meter in Calar Alto, the AR get involved and show interest in that while you offer the telescope. This is a super high chance of getting it. But if only you offer the institute, then you have to pay with money. And if you only offer the telescope, you have less chances. So this bi-modal combination, or how I don't know how to name that, it's a fundamental. So they need to know, that's why they are going to visit first the area that they have a clue on, some of them, because they came from other environments. And they're going later to visit the server. They will make a report to the ARC, and the ARC will decide, but it's a fundamental thing that they see clearly that they have not only good telescopes, but the institute behind that is interested in exploiting significantly the results. And for me, it will be lovely to have it here, obviously. But it has to be you. I mean, you.
Well,
We the people.
let me say that we have only 1 month to try to organize before the committee came to Calar Alto. I suggest that maybe in the different departments we have to talk about our interest, not only in the local volume mapper, but also in the other slow project. In the case that there is interest from the different departments, maybe we can transmit to the directory, to the IAA directory, our interest, and will be for them very useful to see, in fact, that if the institute is interested in this project. So I just suggested to Rubén that at least from the extragalactic department that we can have a meeting the next few days. But I suggest also that other department has to do similar thing and also to talk all together, because it is transversal, not only to one group or to only one department. It is could be of interest for the whole institution. So that's something that we need to do very quick if we want to have some impact for the director, the director, and also they can transmit this the guideline is positive, and they can transmit to the public.
I'm maybe wrong, because I understood that what he's offering to us is the local volume mapper.
No.
No.
No, I'm, you know, as responsible local mapper, I'm talking more about the local mapper because it's the project that I need to push forward. Okay, but the offer is for the whole SLOAN-5 plus after SLOAN-5. So that's what is on the table. Obviously, this is that does not correspond to me. I'm not the leader of the Keith is the leader of the SLOAN-5, but I put after SLOAN-5. So June is the leader of the SLOAN-5. So what I want to transmit is that this offer now, it's again. You get involved, and of course, if you put on the table somehow the telescope, obviously this is a different thing, you know. So I can tell you that technically the 2 meters of Calar Alto is marvelous because it has a coude that you can place the spectrographs in there. The fibers are very short. That's technically it's a good choice. There are other choices, yeah, they're not that good. They have other things to offer, you know. But that's not. It's not decided at all. You know, they don't came. Some of them came from Chile, others came from the USA. They don't came here to see Calar Alto. They have already the decision taken. They have the decision taken. They didn't came. You know, they don't care. You know, it's not what is going to happen. One.
No comment, question?
I freeze you. Well.
We are over time, so perhaps anyone who has further questions can come track you down later.
Okay, yeah, they can address me anyway, whatever they want. Okay. Thank you very much.
We didn't organize